Hello, welcome back. This is section 14.2 of Sergey Lang's Basic Mathematics. And here we're going to go over some formalisms of mapping. So we're going to start looking at what we can do with these mappings. We've already looked at some concepts in different sections of this book. And so here we're going to start with the identity mapping. And we have to define the identity mapping based on its input set, its domain. So the S represents the possible input that we can put into this. So it could be R, it could be R squared, it could be anything like that. And so this function or this mapping will take any of the input and give you back the input itself, right? So this is a mapping that takes S goes to S, right? So it keeps the points that are mapped, or the things that are mapped, remain in the set itself, okay? And we sometimes just omit the subscript S because we understand that the identity mapping has a set that it can work on. It can work on any set, really, if you think about it. Any set you can imagine, there's an identity mapping that will map things back into itself, okay? Suppose that we have two mappings, F, which takes S, elements of S, and maps that to elements in T. And we have a mapping G, which take elements of U and maps that to V. Okay. Assume that T is in, so T is a subset of U. Okay. So T may not have all the values in U, but it has some of them at least. And every value in T is found in U. Okay. Because of this, we can form a composite mapping. And we're going to call that composite mapping G of F. That little circle is not a multiplication. It means we're composing these two functions together. And what this means is we are going to take G applied to F applied to that initial element of S. So we take an element of S, we map it through F to an element of T, and then through T we map it through G from U to V. Okay? And we can do this because every point in T is indeed in U. Okay? Let's get an example here. Okay. He says, let F of X be defined for real numbers such that the mapping is X squared, and let G of U be defined such that it is the sign of that number. Okay. And so we can say G of F of X is the same as G of F of X, which is going to be sine of X squared, right? That's all it is. Okay, another example, let F be F of X is 3x minus 2, okay, and G of U be 1 over cosine of U, or that you might know that as a secant, okay. And so F of G, or G of F, this is going to be 1 over cosine of 3x minus 2. Okay? So let's suppose that we had the mapping, let's use blue here. We had I, which maps elements of S onto itself. Okay? And we also have the function F, which maps elements of S into itself. Okay? And F can be any mapping, and when we compose I with F, that's the same as composing F with I, and that's just the same as F, right? So we should remember that this is basically like adding 0 or multiplying by 1, any of those many discussions on the identity that we've talked about many times before, okay? So I of F would be the identity of F of X, which would just be F of X, right? Because the identity doesn't do anything. F of I would be F applied to X, F applied to the identity of X. Well, that's just going to give you F of X back. Okay, and that's why those things are true. Very trivial to prove that. Composition of mappings is associative. What does this mean? Let's talk about that. What that means, let's scroll that down here. Composition of mappings is associative, okay? What this means is that if we have F that maps elements of S to T, And we had G, which maps elements of T to U. And we have H that maps elements of U to V. Okay? Then when we say H of G applied to F, okay, that is going to be the same as H applied to G applied to F. Okay? And we can prove this rather easily. What does this mean? This is H of G of F of X would be interpreted as H of G applied to F of X, okay, which is the same as H applied to G applied to F applied to X. Let's see, 1, 2, 3, 4, 1, 2, 3, 4, okay. And on the other side, we have H applied to G applied to F of X, which is the same as, let's see, this would be H applied to G applied to F of X, okay, and then inside there we're going to get H applied to G applied to F applied to X, okay, which turns out to be the same thing. So these two are always equal, okay, pretty easy to prove that, okay. Suppose that we had an inverse. So we're going to talk about inverses now, okay. So we have F, which takes elements of S and applies it to T, and then we have G, which applies elements of T and brings them to S. Okay. Now, the nice thing about these two things is when we apply them to each other, when we compose them together in this way, we get back the identity. Okay. Okay. Now, this identity set, because it is going to be operating on the set S, right? Because G is going to give you an element of S. If we did it the other way around, F of G, then we would get back elements of T, right? Because F would give you elements of T. So what this means is we start with F, apply that to some element of S, which gives us an element of T, and then we apply that through G, which gives us an element of S, right? So the identity is going to be the identity of the S set, right? Same thing for F of G, but opposite, okay? Let's look at some examples of this. There are a few. Let's use orangey. So in this, we have R plus denotes the positive real numbers. And so we have a mapping F that takes R plus and maps that to R plus. So the positive real numbers, okay? And this is actually the square. So it's going to take X and turn that into X squared, okay? If F has an inverse function, namely the square root, so G will take any positive real number and map that to any positive real number, such that X of G of X is going to give you the square root of X, okay? So when we take these two functions and apply them together, well, this is going to be G of X is the square root of X, and then F of X is going to take that and square it. So that's just going to give you X back, okay? Should be rather trivial for you to see how, if we did it the other way around, this would be the square root of X squared, okay? And this is nice because they happen to be mapping the same sets, to the same sets, okay? So it's a little bit easier to think of. Let's do another example. This is the exponential function and the logarithm function are supposed to be inverted from each other, right? So we have a log base A of X is supposed to give you X. Scroll that up there, okay? And also log base A of A to the X is supposed to give you X back, right? So those functions are inverted from each other. You can see how the log and the exponent functions are inverted from each other. So if we had F is defined to take X mapped to log base A of X, and G is defined to take X and map that to A to the power of X, then we can see how F of G of X is going to be log base A of A to the X, which is just X, and then G of F of X is going to be A to the log base A of X, which is just going to give you x back. And so these are inverses of each other. When you put these two, compose these two functions together, you're going to get the identity back. We can denote the inverse with special notation. So in this case, we will have f to the minus 1 is the function such that f applied to f of minus 1 is the identity, and f of minus 1 applied f to the minus 1 of f is also the identity. So the inverse is denoted with the exponent of minus 1. Note that if f maps t to s, then f inverse maps s to t, right? So we have to be careful on that sometimes, especially when we're not mapping to the same set. Okay? And so an elementary proof concerning the inverse number can be applied to given the uniqueness of the inverse mapping. Indeed, let's talk about uniqueness. So we have two functions. How am I doing on time? Oh, we're over time now. So uniqueness. So we have the idea that we should have uniqueness among the inverses. So let's say we had f has two inverses. G, which maps s to t, and h, which maps s through t. Okay? And you can prove for yourself, and if you don't remember how to do this, there's previous videos that talk about how to do this. Prove for yourself that G and H must be the same. I'm going to give you a little hint. So G applied to F is supposed to give you the identity. What about G applied to F applied to H? What is that supposed to give you? Okay. The next section talks about permutations, and he mentions it here. Permutations is a long section, and I think I'm going to break it up into 2 or 3, maybe even 4 videos. Very, very interesting videos. Very, very fun. But we want to talk about what happens when we iteratively apply f on itself. So f applied to f, we're going to call that f squared. And then f applied to f applied to f, we're going to call that f cubed. Okay? And indeed, f to the n is going to be f applied to f applied to f applied to f, a total of n times. Okay? This shouldn't be new. It shouldn't be too complicated to understand what's going on here, where we're going with this. Indeed, we can say that f of any number k, any integer, positive integer k, plus 1, is going to give you f applied to f k times. Right? That should be rather easy to see. Okay? Here's an example that he uses. I like this example. This is kind of fun. So remember when I was telling you that addition is really a function? Well, in this case, we're going to have the function f of x that just takes x and adds 1. Okay? So what would f squared of x be? Right? F applied to itself twice. Well, we take x plus 1 and we put x plus 1 on the inside, so we get x plus 1 plus 1, so this is x plus 2. Okay? What about f to the k of x? Well, we've done that k times, so we get x plus k. Right? Pretty easy stuff. That's kind of fun. Okay? Suppose we had f that maps points of the plane. So we have, he uses capital F, which maps points in the plane to points in the plane, such that f of the xy coordinates of the point in the plane is going to give you x plus 3 and y minus 4. Okay? And so f applied to itself twice is going to give you x plus 6, y minus 8. That should be rather obvious because we're going to take x plus 3 and put x plus 3 in there. We're going to take y minus 4 and put y minus 4 in there, so it's minus 4 minus 4. And indeed, you can just reason out for yourself why it's going to be that doing that k times with some positive integer k is going to give you x plus 3k and y minus 4k. Okay? This is pretty powerful stuff. Okay? Another example. This one's pretty easy. So he says f maps points in the real set of numbers to points in the real set, or f maps real numbers to real numbers, and it's given by x cubed. So f squared of x is just going to be the cube of the cube, or x to the 6th. And indeed, f to the k of x you can work out would be x to the 3k. Right? Pretty easy stuff. Okay? F to the m plus n is the same as f to the m, is the same as the composition of f to the m and f to the n. You can see why, because this is fm times, that's fn times, and so it's going to be sum f to the m plus n. What about f to the 0? So we're going to choose, because we're saying in rational people, that f to the 0 should be the identity, right? Why is that? Well, if we had f to the k applied to f to the minus k, right? What would minus k mean? Well, f to the minus k, that's just f to the minus 1 applied to itself k times, right? And so what happens is each of these k's cancel each of those k's out, and you get the identity, okay? And that is why f to the k minus k, which is equal to f0, okay? Pretty easy stuff. Oh, he says that he hints at using induction to prove what we've just done here. Induction is a method of being absolutely sure that you haven't missed anything in the proof. It's rather simple to do. It's rather fun to think about. And that's going to come later in this book. Okay? Example, let f be the function mapping real numbers to real numbers, such that f of x is defined to be x plus 3. Okay? So f to the k of x is x plus 3k. We've already seen that. What about f to the minus k of x? What is that? Well, we have to, f to the minus 1 would invert this. So the function that we plug into x that would invert this would be x minus 3. So this is going to be x minus 3k. Okay? And you notice that when we put these together, f of k composed of f of minus k, when you put in x, well, we're going to get x minus 3k plus 3k, and the 3k's will cancel, so we'll just get back x, which indeed works. Okay. Inserting special numbers in the above formula. We can do this, so we can say f of 5 applied to f of minus 3. That's the same as f of 2, which should be x minus x plus 6, right? Well, f of 5, I have to put the x here because that's we're applying this to x. So f of 5 of x is x plus 15. F of minus 3 of x is x minus 9. And so when we put this one into there, we get 15 minus 9, and that indeed does give us 6. So everything works the way it's supposed to do. Let's suppose that we have a mapping, okay, such that f of m is equal to f of n. And I don't know what that mapping is going to look like or how that's going to behave, right? What this means is that if we compose this with f of n minus n to both sides, minus n is equal to f of n composed with f of minus n, then we're going to get f of m minus n is indeed the identity. Okay? So if you did have such a magical function, I can't think of what that would look like at this time. Maybe you have an idea. If you do, comments below. And when you compose this with m minus n, that's actually identity. Okay, so if we had, let's say we had f to the 5th is the same as f to the 3rd, then that means f squared is actually the identity. So f applied to itself gives you the identity. It's pretty amazing stuff there. Okay, we're going to have a series of functions now. Okay, f1 all the way up to fm. And these are defined such that any of these functions, f to the I, applied to itself gives you back the identity. What would be the inverse of f1 applied to f2 applied to all the way up applied to fm? What would be the inverse of this? If we were to find the inverse, then it would be a function or mapping f where you compose that with f and you get back the identity, right? So this would be f, okay? What do we have to apply to get back the identity? Well, if you think about it, if we applied f to the m minus 1, so we said f is equal to f to the m minus 1 applied to f to the m minus 1 all the way down to f to the 2 minus 1 applied to f to the 1 minus 1. Okay, you can see here how the inside circle will cancel and then work its way out, and you'll get the identity in the end. Okay, so when we take the inverse of a series of functions that are applied to themselves, then we need to reverse the order of the inverses of those functions. Okay, that is a procedure that we're going to be using in the next section heavily. Guys, thank you for watching. I know this video was a bit long. Hopefully it's a little bit interesting to start thinking about functions this way. Hope you guys have a great day. Take care, and bye-bye. This video was part of my series on Basic Mathematics by Sergey Lang. Be sure to subscribe and ring the bell, like and share this video. You can find me on Discord and support me on Patreon. Thanks a million.